Hey, welcome back, grade 11 chemistry students. This flipped lesson should complete topic 4. It should complete topic 4, which is bonding. Remember, we are talking about intermolecular forces, and there are 3, of course, main intermolecular forces. We know this: London dispersion forces, dipole-dipole forces, and hydrogen bonding. We've covered these first 2. I want to also say that I did check your work on the IMF practice worksheet, right, for polar or nonpolar molecules, and it looked pretty good. But I say, yes, please follow instructions. So the instructions say to state whether the molecule is polar or nonpolar. You need to do that. So I saw some very nice sketches, but then I didn't see any conclusions. So you will lose points that way on an assessment. So you must follow all instructions to the letter. Also, the second part of that practice worksheet was to choose 3 of, I believe, 5 examples, and then compare your predictions with literature values of dipole moments. And again, when it asks you to compare, you need to actually do that and say something about your prediction versus what you found. You can't just simply put a number down or put a reference down. That's not a comparison. Okay? All right. Let's talk about hydrogen bonding. All right? And let me give you an example of just how significant this is. And let me say also that hydrogen bonding, which is a very bad name because it's not true chemical bonding, as far as we know. It is considered an intermolecular force, or even an intramolecular force, as we will see. But hydrogen bonding has got to be one of the most important principles in chemistry, biology, biochemistry, molecular biology. It revolutionized our understanding of molecular interactions, drug mechanism, DNA, protein folding, enzyme activity, enzyme selectivity, you name it. Extremely important topic. But let's take a look at a very simple example. Here I have 2 molecules, dimethyl ether, this guy here, and ethanol, this guy here. Dimethyl ether is a gas under standard conditions, standard temperature and pressure, and boils at minus 24 degrees Celsius. So it is a gas all the way down to minus 24 degrees Celsius, at which point it liquefies. Ethanol is a very, very well-behaved liquid under standard conditions. It doesn't boil until 78 degrees Celsius, which is way, 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 way hotter than you will ever experience on planet Earth, right? So ethanol is a liquid up to fairly high temperatures, right? Big difference, over 100-degree difference between the boiling points of these 2 compounds. Now, what I want you to tell me as a homework assignment, you're going to think about why this is such a good comparison. Why is this such a good comparison? Okay, remember, we're talking about hydrogen bonding, right? We know these other forces can also operate. Why is this such a good comparison? You're going to figure that out. All right, let's look at water. You know that water, you've heard this many times. Water is an amazing substance. But what does that really mean? Well, take a look at this. Water is a tiny, tiny molecule, H2O. It has a molar mass of 18 grams per mole, right? It boils at 100 degrees Celsius. Look at some other comparable formulas and molar masses. Methane at 16 grams per mole boils 260 degrees lower than water. That's amazing. That's a huge difference. Ammonia, 17 grams per mole, which begins to look like water now. H2O versus NH3. Minus 33, 130 degrees difference. Hydrogen sulfide, which has almost twice the molar mass of water, right, boils at 160 degrees less than water. And remember, boiling point has to do with how strong are the forces that hold the molecules together in the liquid state, right? So there are tremendously greater forces operating between water molecules than between any of these other molecules, and those forces are hydrogen bonding forces, and they're very, very significant. Okay, what do you need to have in a molecule to have hydrogen bonding? Well, it's based on the bond XH, where X is either oxygen or fluorine or ammonium. Not ammonia, but ammonium. So X is a very electronegative element. It involves polar covalent bonding because X is an electronegative element and hydrogen is not. The difference in electronegativities make this a polar covalent bond. But it's a very special polar covalent bond. It's one that involves hydrogen. We can talk about hydrogen bond donors and hydrogen bond acceptors. Let's go right to a picture. Here is a picture, a representation, of the hydrogen bonding in ethanol. Okay? Now remember, we looked at ethanol here, and it had a much higher boiling point than dimethyl ether. And so what you see with these dashed lines, those are hydrogen bonds. And notice that in every case, they're intermolecular between molecules, and they connect the oxygen of one ethanol to the hydrogen, which is bonded to the oxygen of another ethanol. In every case, that is true. You don't ever see red lines between, you don't see dotted lines between two red oxygen atoms. You don't see dotted lines between two white hydrogen atoms. It's always between a red and a white. A red and a white, a red and a white, a red and a white. Okay? So this is the hydrogen bonding network of ethanol in the liquid state. Here's water in the liquid state, right? And when we talk about hydrogen bond donors and acceptors, and we go back to ethanol, in this particular case, this is a hydrogen bond acceptor, hydrogen. I'm sorry, that's wrong. This is the hydrogen bond donor because it's providing hydrogen and it's being accepted by oxygen. So we have hydrogen bond donor, hydrogen bond acceptor, right? Here for water, we have hydrogen bond donor, that's a hydrogen, H2O, OHH, that's the hydrogen bond donor, that's the hydrogen bond acceptor, and again, between water molecules, the dashed lines are O's between the white hydrogen and the red oxygen. These are hydrogen bonds, the hydrogen bonded network in water. And notice something, that you can have more than one dotted line connecting a single atom. So for instance, this oxygen is a hydrogen bond acceptor both here and here, right? So it forms this very, very complex structure. It's funny to say that liquid water has structure, but it has structure. Liquid water has organization, it has structure, as opposed to liquids that do not hydrogen bond. Now, these bonds are constantly shifting and making and breaking, but at any given time, if you took a photograph of this, you would see trillions and trillions and trillions of these interactions. What else can we say about these hydrogen bonds? Well, first of all, this is one more picture. This is ethanol in water. Now, ethanol mixes with water in all proportions, in all ratios. And one of the reasons it does that is because ethanol is water-like and can displace a water molecule and can participate in the same kind of hydrogen bonding. So it doesn't upset, right, pure water, which is why it can mix with water in all proportions, right? This is basically aqueous ethanol that you see here with its hydrogen bonding interactions between water or between itself. All right, now, what do we see in this screen? What we see is that there are other requirements for hydrogen bonding. For one thing, the three atoms must be linear, must have linear geometry, right? So in other words, the electronegative atom bonded to the hydrogen, covalently bonded, polar covalent bond to the hydrogen, donating the partially positive hydrogen, the delta plus, to the electronegative atom acceptor, donor acceptor. Those three atoms have to be in a line. Okay, they have to be linear. That's one requirement. Another requirement is the length, the distance between the hydrogen that's being donated and the oxygen that's accepting the hydrogen has to be a certain distance. And here you have 1.8 angstroms. And an angstrom, this by the way, one angstrom equals 100 picometers. So this is about 180 picometers. 180 picometers. You can see that an actual bond is more like 100 picometers. So this is about twice the distance of a normal covalent bond, right? And this can vary. It can be 1.8, it can be 1.9, 2.0. But at some point, if the distance becomes too great or too small, for whatever reason, that hydrogen bond won't form. That's a requirement. Okay. Then there's a whole area of intramolecular hydrogen bonding. Intramolecular, within the same molecule. So this is the molecule orthonitrophenol. That's a benzene ring. There should be a circle here, and there should be a circle here. And what you see is that the preferred shape of this molecule, right, which has an OH here and an NO2 here, right, the preferred shape of this molecule is to have these atoms organize themselves or arrange themselves in this ring, in a six-membered ring. Same thing is happening here, right? So that changes the shape and the properties of these molecules. This is an intramolecular hydrogen bond. Okay? And what you can't see in this picture is that these atoms, or this geometry, is such that the H, the O, and the N are, again, they're collinear. Now, this is a six-membered ring, so it's possible to have these three atoms be in a line. Okay, you can't really do that with a smaller ring size, which is why these intramolecular hydrogen bonded structures tend to be at least six-membered rings, if not greater. Intramolecular hydrogen bonding is absolutely essential to biology. Absolutely essential. Your proteins, which are your enzymes, they fold into a certain very specific shape, and they do that. They do that largely due to hydrogen bonding interactions between amino acids, right, that are far apart in terms of their sequence number, right, on this chain, on this protein chain, okay, but actually begin to interact and pinch this chain close to form a loop, and this gives the protein the correct structure or shape to function as an enzyme. So this whole area of protein folding, which is fascinating, protein self-assembly and enzyme structure and enzyme active sites and enzyme selectivity, right, has to do greatly with intramolecular hydrogen bonding. Your DNA, right, DNA is what? It's a double helix. It's two strands of these nucleic acids that are all covalently bonded together, and then those two strands interact. These are all hydrogen bonds. This is intramolecular hydrogen bonding between a guanine and a cytosine and an adenine and a thymine. You study this in biology probably. Okay, so it doesn't get any more important than this. So hydrogen bonding is immensely important in biology, especially intramolecular hydrogen bonding. And again, we will practice this quite a bit. It's so important. And that's all for now.